we're going to look at are the intercepts of rational functions. Ian, what kind of intercepts do we have for functions? What are they called usually?
They're called x and y intercepts.
Yeah, the x and y intercepts. Joe, what are the x-intercepts really called though? What are the x-intercepts known as? The what? What are the x-intercepts known as? What's another word for them?
X-intercepts. I don't know what you're asking.
There's another word.
X-intercepts.
There's another word for the x-intercepts. What is it? Who can help them out? What's the word for x-intercepts that we use? The what of the function? The zeros of the function. So we are really finding the zeros. The zeros is the word you're looking for, Joe. Okay? So for this problem, we're trying to find the y-intercept to start. Let's go easy. The y-intercept is easier. Please recall the following. To find the x-intercept, set y to 0. To find the y-intercept, set x to 0. So to find the y-intercept of this equation, set x to 0. Isn't it simple? Take a look what happens. 0, 0, 0. Those drop off. You're left with negative 3 over 6, which is negative 1/2. So the y-intercept is 0, negative 1/2. Easy enough? Does everybody see that? Is that clear? Can somebody make a correlation already? The y-intercept will always be what? Give me a generalization. Sure, that's one part, but that's something we've always known based on this.
It will always be the c values over each other.
Perfect, Jared. It'll be the ratio of the constant terms. See how it was negative 3 over 6? It doesn't matter. Any polynomial, all the x's drop off because they're 0. So what are you left with always? The constants, the c values. Well done, Jared. And I didn't make that generalization until the second one. Okay? That was the conclusion. So take a look at the second one, read through it. Read through it, make sure it makes sense. Then we'll go over it. Remember, the stock is valued in millions, so it's 1.75 million. Does the conclusion make sense, the way it's worded? Yes? Anybody not understand what the second problem is doing and the conclusion? This is the easy part of today's lesson. Okay, the tougher part is finding the zeros, but it's actually quite simple because we've done it so much already. We found zeros of quadratics and quartics and cubics and anything. Okay? All right, let's take a look at number 3 now. Number 3 says to determine the x-intercepts of the following rational function. Okay? So take a look at this problem. Always start by factoring. Remember we talked about factoring? We always want to factor so that we can find something when it's equal to 0. Well, Joe, how do you find the x-intercept? Set?
Y 0.
Yeah, so take a look at the first line, everyone. Setting y to 0, that's what you get. But it doesn't help to look at it this way, so look at it in factor form. How do I get rid of this 2x? Multiply by 2x on both sides. Well, think about it this way. What is 0 really? 0 is 0 over any number. Agreed? So if you ever have some fraction equal to 0, the numerator must be 0. Would you agree with me there? To get 0 as a fractional answer, it's got to be 0 over 5, or 0 over 7, or 0 over 2. So we could set the numerator equal to 0. Does everybody see that? To find the zeros of this function? So setting the numerator equal to 0, we get 2 different answers. So we have 2 zeros of the function. So what are the x-intercepts? 5, 0, and negative 2, 0. Okay? Notice the denominator had no effect on the problem here. In a minute, we're going to see when it does have an effect. Any questions on this one? Is this pretty clear? I feel like you guys have done so much this year with roots and zeros, right? That it's like by now, it's like, all right, I can do that. It's just factoring. Okay, it's just a little bit new now because you have a denominator involved. Example 4. A particle's movement is represented by the velocity function given by v of t equals the quantity t squared minus 5t plus 6 over the quantity t minus 2. Determine when the particle is at rest. it mean when something is at rest? What's the velocity if I'm standing still? What's my velocity, everybody? 0. So when I ask you to find when the particle is at rest, you set the velocity equal to 0. So plug in a 0 for v of t. So what are you really doing? When you said v of t equal to 0, aren't you finding the what? Okay, the initial conditions in a sense, sure, but when the function equals 0, you're finding the roots, or you're finding the zeros again. So you're still finding the x-intercepts, but it's a function of t now, right? So you're finding the t-intercepts. But what do you notice happens here? What did I do with this equation when I factored it? What did I do with the function when it was factored?
Oh, you canceled the t minus 2.
Because what happens when you're factoring the top and the bottom? What's there?
Hole.
A hole. Remember, a hole exists in a graph when there's a numerator and denominator with the same factor. So you can't have a hole and a 0. It doesn't make sense. A 0 is a defined point that occurs on the x-axis, whereas a hole is an empty circle. You cannot have both of them. The hole trumps the 0. So by default, this is a hole, so get rid of it and then solve what's left over.
So there's a hole in the graph if it's 0 over 0.
Yes, exactly right. Or you could see it as the same factor in the top and the bottom, okay? But it's 0 over 0 when you evaluate, yes. So what we get is t minus 3 equals 0, this part right here. So what happens? At time equals 3, the particle is at rest. Okay? Joe, you look like you have a headache. You need to get a glass of water? You sure? Okay. Let's take a look at example 5. Example 5. Who can step me through this? And I know the answer's there, but tell me what's happening in your own words. What's happening with example 5, Ryan?
The numerator they factor out x.
Louder, Ryan.
In the numerator they factor out x.
Before that, though, what did we do? You're finding the zeros. So you have to set it equal to
0.
0. Thank you. And then,
You factor out x.
good. Continue.
And you factor in trinomial
Good. Which becomes
x plus 9, x minus 3.
good. That's on the board. Very good. Keep going.
And you cancel the x minus 3. That's
Because they are.
whole.
That's a whole at x equals 3. Good.
And then you make x parentheses the quantity x with 9.
Because that's what's left right there. Good.
And then you solve for it.
Okay. So your zeros are 0 and negative 9. Remember, if I ask you as coordinates, he says, what are the zeros? If it says, what are the x-intercepts? Your answer would look like this. Those would be the x-intercepts, okay? But we're just finding the zeros of the function, so you don't have to. In example 6, I want you to find the x and y-intercepts.
Doesn't technically x cancel off?
Say again?
Doesn't x on the outside cancel off when you make it equal to 0?
No, because remember, Ryan, this is a t-chart. You have to set each factor equal to 0 and then solve. Remember how we do this? You set each factor equal to 0 and then solve. How do you solve this? It already is solved. X equals 0. That is one solution.
The x on the outside.
Yeah, that's what I'm talking about. That x right there goes there. The x plus 9 goes there. These are factors.
Oh.
You can't just drop it off anymore.
Okay.
Okay, they're factors. Go through example 6. See if you can actually do it. Because I didn't show any of the steps in there on purpose. I want to see if you can do it. How do I factor that numerator? Synthetic table. So go ahead and try and figure it out on your own. Try and come up with those 4 factors using a synthetic table and testing possible factors. You're welcome to use the rational root theorem to look at the values of 30, or the factors of 30, right? And those are your possible roots you can test. So 30 and 1, 15 and 2, 10 and 3, 6 and 5. You can try any of those as a synthetic table. And there's 4 factors that do work. Show that they do work on your own. I'm going to pause the video. So the vertical asymptotes come from the denominator. Well, one of the vertical asymptotes is x equals 0. That's how you smile. One of the vertical asymptotes is x equals 0, which means, what's the line x equals 0 look like? Here's the axis, right? Here's x equals 1. Here's x equals 2. Where's x equals 0? It's the y-axis. So if the y-axis is an asymptote, that means that the curve can't touch the y-axis, right? So is there going to be a y-intercept? No, there's not. And this is our proof of it right here. The y-intercept is undefined. There is no y-intercept. D-N-E. It does not exist. It does not exist simply because there's a vertical asymptote there along the y-axis. Okay?